Welcome to our third lab. This lab will be taught in two different parts. This is the first part. We will present the variable data types used with Teensy. Moreover, it regards learning and using the standard libraries that allow you to input, in other words read, and output, in other words write, digital and analog signals with Teensy's 3.6 GPIO, which stands for General Purpose Input and Output. Overall, in this lab's first part, you will learn about data types, I/O functions, both analog and digital, and time functions. All of the former are parts of a standard library. In general, standard libraries typically include definitions of commonly used algorithms, data structures and mechanisms for input and output. Our goal is to set the right background for you in order to proceed later on with the other session of Lab 3 on using Teensy's GPIO pins. Lab 2 introduces you to variables, for example LED, data types, for example int, I/O functions, like output, and other functions, specifically pin mode, digital write, and delay. In this lab, we will explore further types and examples, so that you can write more advanced programs. Let us start with the key concepts and commands for programming, variables, and data types. In most programs, some type of calculation needs to be performed on data. Such data are stored in a variable. When declaring a variable, the compiler allocates a specific amount of memory depending on the data type. Assuming that memory can be logically presented as a table, like the one in the example on the slide, then the LED variable would take one cell of the memory, assuming that one cell has 16 bits, which is as much as needed for an int variable. Had the size been, for example, 8 bits, then any int variable would need to be allocated with 2 cells in the memory table. There are different types of data, each one coded with a different number of bits. To ensure the proper amount of memory is allocated, you must tell the compiler exactly what sort of data you want to store. This table summarizes the different types. First and foremost, you got a void type. This is a special case. You will see in practice that sometimes you do not want to specify a data type. In addition, remember that apart from variables, functions may also return a value, which it can be of any type, for example int, including void in case the function does some job but returns no result after calling it. Boolean. This type is used for logical processing. It takes values that mean either true or false. Char. Char encodes one character as an ASCII number. For your own information, ASCII stands for the quite simple and old American Standard Code for Information Interchange, which maps characters to a number. For instance, character 0 equals the number 48. Unsigned char. No bit is used for signing the number as negative. This means that we can leverage the first bit for doubling the range of code numbers for char variables. Therefore, variable codes are in the range of decimal numbers from 0 to 255. Byte. 8 bits. This includes decimal numbers from 0 to 255. Int. Decimal integer numbers within the indexed range in the table. Unsigned int. Decimal integer numbers with no bit used for signing negative values. Hence, the maximum value is 2 times that of an int, from 0 up to 65,535. Word. Again, decimal numbers within the same range. Long. This type is used for very big integer numbers. Unsigned long. for even bigger ones. Short for decimal numbers. Float. Float is used for floating point numbers within the indexed range in the table. Double. Double is another floating point number, but double the size of a float. String. String is used for an array of char variables. String again. Notice the capital S. This is used for advanced arrays of char variables. And finally, array. In case you wonder what an array is, it is a collection of variables. When declaring a variable, first specify the data type and then the variable name. Always finish with a semicolon. Optionally, you may assign a value by using the equal sign, such as in the case of int pin_number equals 9 semicolon. Serial output. One way of accessing data on a microcontroller is by programming it to send the information over a serial connection, where it can then be received by a PC, which can in turn display the results. The IDE has its own serial communications interface, which can be accessed when a program is running by clicking the magnifying glass icon, the one on the top right. Now let us see how we can print data. To do so, we are going to write a short program. Go to the menu bar and click on File, New. The figure shows the code to be written. First, we create a variable to store the data. To send this data, serial communication is initialized at the setup function using serial.begin. Serial.begin takes one argument that specifies the communication speed, which is otherwise known as the baud rate. The baud rate specifies the number of bits transferred per second. Faster baud rates enable transmitting more data in less time, but may introduce transmission errors too. 9600 baud is a common value. Teensy 3.6 uses the maximum rate possible across the USB connection. Once serial communication is initialized, headers and data can be sent using serial.print. Serial.print prints a tab when you use /t as its argument. Serial.println without any arguments starts a new line. More formally, it adds a carriage return. To save the program you wrote, go to the menu bar and click on the Save shortcut or Ctrl+S or File, Save. Connect Teensy to your computer. First, verify your program. Once verification is finished, you are prompted to press the button to manually enter the program mode. Then upload your program. Finally, click the serial monitor icon of the IDE. You should be able to see the output as shown in the middle. And now it's time for our lab's activity. In the previous program, we defined our variable as an int. Nonetheless, we could have used other data formats, such as long. What happens if instead of an integer number, you use decimal numbers? For example, what if the initial value of the variable number is 1.52? Also, try different, non-numerical data types, such as char. What happens in this case when running the program? Try to answer these questions in a short summary of 50 to 70 words. Let us proceed with the input and output functions now. Teensy has a series of pins with which it can interact with the real world. This is commonly referred to as input and output, or abbreviated as I/O. Pins can be defined as either being an input or output. Pins can also be classified based on the type of signal they can read or write: digital and analog. As its name indicates, digital I/O uses digital signals. Teensy 3.6 has 3.3 volts for a logical 1 and 0 volts for a logical 0. Examples of digital inputs include switches and push buttons. They are either on, in other words closed circuits, or off, in other words open circuits. There are no values in between. Pin mode is used to configure the pins as digital inputs or digital outputs. It uses two parameters, pin and mode. The pin parameter is the digital pin number to set. When your sketch begins, all digital pins by default are set to input mode, and you can change that by setting the mode parameter value otherwise. Input obviously sets the pin as an input pin for your sketch program, whereas setting a pin to output allows to make its status high or low by calling digital write. Regarding input pull-up, pins have a pull-up resistor. Pull-up resistors are useful when connecting push buttons that can connect the pin to ground, but when the button is not pressed, there is no connection at all. The pull-up resistor causes the voltage to be high when nothing is connected. Let us start with input. Pins configured as input can read voltage applied to them. Pins configured as input with nothing connected to them are prone to change state due to electronic interference. For example, static discharges. When connected to a switch, like the one in the picture, pull-on resistors are commonly used to pull the pin down to a low state. Digital read. Digital read is used to read the state of a digital pin. The parameter pin is the pin number to read from. Here is an example. Our result variable gets the result of calling digital read on a specific pin. This function returns either high or low and stores it in the variable result. Digital write. Digital write is used to write the state of a pin that was declared as output. The pin parameter is the pin number to write to, and the value parameter is the logical level you want to write, either high or low. Microcontrollers are digital, but some of them, like Teensy 3.6, can read analog values. The device used to read analog voltages, as shown in the figure, is called an analog to digital converter, or ADC. Analog pin is used to read the voltage value on a pin. This is specified in the pin argument and the value is returned as an int. Analog write is used to write an analog output on a digital pin. It is based on pulse width modulation, PWM, which emulates an analog voltage by rapidly switching between 0 and 3.3 volts. It has two arguments, the pin to control and the value to write to it. PWM pins can turn on at different intensities, from 0, in other words, fully off, to 255, in other words, fully on. Let us proceed with time-related functions. Timing is important for all electronic systems. Electronics are not instantaneous, and most sensor components require some time before they can be accessed. Namely, one-wire humidity sensors typically require 100 milliseconds of time between acquiring a reading and returning the result. Likewise, tracking time can be very useful in battery-powered systems, as it can provide some indications on how much power has been already consumed by the system. For example, the time that the program has been running and thus the Teensy being on. Delay time is used to tell the microcontroller to wait for a specified number of milliseconds, as specified by the time parameter value, before resuming the program. The function can be used to tell the microcontroller to wait, for example, before reading a sensor or for slowing down a fast loop. Delay microseconds is likewise to delay, but uses microseconds instead. Millis is a function that returns a number of milliseconds as an unsigned long. This function can be used to check how long the current sketch has been running, or to calculate how long a function takes to run by comparing the number of milliseconds before it starts and after finishing. Micros is almost the same as millis, only using microseconds rather than milliseconds, returned again as an unsigned long. And with that, we have reached once again at the end of this lab session. Don't forget about this lab's Lab 3.1 activity. What happens if instead of an integer number, you use decimal numbers? For example, what if the initial value of the variable number is 1.52? Also, try different, non-numerical data types, such as char. What happens in this case when running the program? Try to answer these questions in a short summary of 50 to 70 words. And to wrap up, in Lab 3.1 you have learned about data types, I/O functions, and time functions.